Let's talk about continuity of a function. Continuity. Now, in order to address continuity, we have to first review one-sided limits and limits. More specifically, we want to answer the following two questions. Question 1, when does one-sided limit exist? Okay. And question 2 will be, when does the limit exist? The second question will be easier to answer once we figure out how to answer the first one. Now, to discuss when one-sided limits do exist, actually it's easier to talk about the case where the one-sided limits do not exist. So let me show you two cases where one-sided limits may not exist, and from that we can say if it's not of these cases, we know that the one-sided limit does exist. Okay, one-sided limit. Okay. All right. The first case that one-sided limit may not exist is when at a point A you have a vertical asymptote and the graph is going towards to infinity or maybe negative infinity. So let's say your function f of x has the graph that looks like this. In this case, you have limit of x going to a minus of f of x going to infinity, and also if it's going down like that, it will be negative infinity. And in such a case, we say that the limit does not exist, or another way to say it is the limit diverges. The second case where the one-sided limit may not exist is more exotic. It doesn't happen that often. Is the case where you have the function oscillating wildly. So it's better to explain this by using an example. Say y is equal to sine of 1 over x. Okay. We all know that sine is a periodic function, so if you have sine x, as x goes through all the angles of a circle, it goes up and down and up and down, and that's because in the unit circle, at any point, the sine is the y coordinate of this angle. So as you go around, as the angle goes from 0 to 360, it goes up and then down and negative and comes up. Okay, so if you drew the graph of the sine for 720 degrees, it's going to go up and down twice. Just like that, if we think about what happens to sine 1 over x, this time when x gets closer and closer to 0, then 1 over x becomes a very large value. If x is a small positive number, this is a very large value. So as x goes to 0, this will go through all the angles. It's going to go through the circle very rapidly. And if you use the graphing calculator to draw this graph for the right side of the graph, it's going to look something like this. So all the highest points will be 1, all the lowest points will be negative 1. But as it gets closer and closer to 0 from the right side, you're going to get wildly oscillating behavior. So in this case, we say the limit of x going to 0 plus of sine of 1 over x diverges or does not exist because it oscillates wildly. Okay. All right, and then we say if it's not of these two cases, then the limit, one-sided limit, does exist. So a success example will be when you have something like this. The graph would get closer and closer to a certain value as it gets closer and closer to a, and let's say that value is b. In this case, you can say that the limit of x going to a minus of f of x is equal to b. In this case, you say it converges. Okay, so that's the answer to the first question. When does one-sided limit exist? If the function value gets closer and closer to one specific finite value, then the limit does exist. And the way it can fail is when it goes to infinity or when it oscillates wildly as you go near that value. Now we are ready to talk about the second question, which is when does the limit exist? Let me write that down. Number 2, question, when does the limit exist? Well, the condition is that first, limit of x going to a minus of f of x should exist. And since we've already discussed when a one-sided limit can exist, we know what this means, okay? And also, the other side limit should exist too. So a plus of f of x should exist. And the second condition is that once you've established that the left limit and the right limits do exist, you have to make sure that they give you the same value. If the left limit is same as the right limit, then you say the limit does exist. Okay. Often, it's just enough to state the second condition, because if you just have this second condition, it already means that, oh, this left side should exist, the right side should exist, and they should be equal. So you can just write this one single condition as the condition for the limit to exist, and you can interpret this single equation as exist, and they should be equal. Okay, that's how you say the limit exists. Okay, so whenever you want to show that the limit does exist, then you should try to show this is true. Okay, so for example, if you have a jump discontinuity at A, point A, then since the right limit and the left limit converge to different values, okay, if let's say this is B and that's C, then we know that the limit of x going to a minus of f of x is B, whereas limit of x going to a plus of f of x is C, and these two are not equal, and therefore in this case the limit does not exist. Okay, and the case, so this will be the fail case, and the success case will be when you have something like this. Okay, I mean you may have a value here or not, or it may even have a different value. It doesn't matter. So at point A, if this is B, in that case, limit of x going to a minus of f of x is equal to B, and it's also the same as limit of a plus of f of x. So they're equal with B. In this case, we say that the limit of x going to a of f of x is equal to B. Okay. All right. So that was the review of when one-sided limits do exist and when limits exist. Now we are ready to talk about continuity. Okay, what is continuity? Intuitively speaking, it means intuitively, graph is not broken. Or another way to say it is, the graph is connected. Okay, so if you see a graph connected at a certain point A, then you say that the function f of x is connected at A. So here's an example. Suppose you have a function like this, and this is the location A, and as you can see at A, the left side and the right side is connected. So this is the case where you say f of x is continuous at x equal to A. Now let me show you when it fails. So there a few different ways to fail. One possibility is when you have a jump discontinuity, like this. Okay? So if the limit does not exist, if you have a jump discontinuity, then the graph is broken. It's not connected. Therefore, it's not continuous at A. It is continuous at other points. It's connected at other points. So if this was B, and then you can say the graph is connected at B or this other point. But at A, the graph is not connected. Therefore, it's not continuous at A. And for this type of discontinuity, we say it's a jump discontinuity. Okay, another way that you can have fail is when you have the value just missing at that point. Okay? So if the value of the function is missing, it's not there, then you have a hole. So the f of A is undefined, and that leads to not continuous at x equal to A. So we say f of x is not continuous at x equal to A. Okay. You may even have a case when you do have the value at A, but the value of the function is different from the limit. Okay? In that case, this is another case of not continuous case. Okay? It's another case of failure. Now, looking at these, you can come up with the simple criteria, or actually it's the mathematical definition of continuity. We say a function is continuous if first the limit has to exist so that you don't have any kind of jump discontinuity. So f of x, when x is sent to A, this limit has to exist. And the value has to also exist, or else if it's empty, then you'll have a broken place. So the value at A should exist. And to make sure this third kind of case doesn't happen, we say that the limit of fx as x goes to A should agree with the value of f at A. If these two agree, then they can't be different, so this has to be brought down here, and it's going to be connected if this happens. So you can take this as the definition of continuity. So this is the definition of continuity at x equal to A. Now, just like before, when you see this definition, it really means three things. First, the limit has to exist. Second, the value has to exist. And third, those two values should agree. So those three are the things that you have to actually make sure it holds in order to show that something is continuous. All right. Now, these two cases of discontinuity, we say this point right here is called RPOD for short, and it really means removable point of discontinuity. Okay, so we say these points are somewhat curable if you define the function value to be equal to the limit. Then it's continuous, right? Jump discontinuity is not a removable discontinuity because you can't just redefine the value, bring this point to somewhere to make this connected. In order to make this connected, you actually have to take a portion of the graph and bring it down, and that's harder. So we call this case as RPOD, whereas this one as jump discontinuity. And that's the introduction to continuity.